Hey everyone, welcome in for a special proteomics video. So I understand there's been a little bit of difficulty in treating the data that we collected for some of our enzyme kinetics experiments, so I wanted to make this hopefully instructional video that should kind of help you out a little bit with some of the most troublesome issues. Okay, so let's start with some of the more basic calculations that you need to do before you can start doing Michaelis-Menten plots and Lineweaver Burke plots. So what you did is that for a particular run, you collected absorbance versus time data for each concentration of substrate that you tested for your enzyme. So what I'm about to show you is a set of calculations and plotting that you'll have to do for every substrate concentration that you tested during a particular run. So for one run, I think we did, let's see here, I think we did 0.05, 0.1, 0.2, 0.5, 1, 5, 10, and 15. That may not be exactly what we did, but those might be some of the substrate concentrations that we actually tested. So let's say that we're doing this for our first substrate concentration of 0.05. So this is the run that we collected for our enzyme at this particular substrate concentration. So we have 90 seconds worth of data that we collected, and we collect the following absorbance values. Okay, so what we want to calculate for this particular substrate concentration is the initial velocity, meaning that we're talking about the number of micromoles of substrate converted to product per minute early on in the reaction. So approximately the first minute or minute and a half or so. Okay, so the first thing that we want to do here is we want to create a XY scatter plot from this. So I'm going to go to chart here and go to XY scatter. Looks like a pretty good straight line, so that's good. Okay, so I'm going to create a trend line because we need the slope here. So I want to get Microsoft Excel to give me the equation of the line. There we go. Okay, so I don't really care about the y-intercept here because the y-intercept should be 0, because if there's in an ideal world, you should be able to get an absorbance of 0 at a time of 0. It doesn't always work out that way, but we don't care about the y-intercept. We only care about the slope. The slope here is telling us the change in absorbance units over a change in time, meaning absorbance units per second. So we want that slope. So we're just going to quickly put in a cell for that slope, which is 0.0025. That is absorbance units per second. We want micromolar substrate per minute. So the first thing that we want to do is we want to change this, which is, we'll just kind of go AU per second here. We want this first in AU per minute. So we're just going to multiply that by 60 seconds per minute, right? Okay, there we go. Okay, so that is absorbance units per minute, and that kind of seems to check out because in about a minute, that's about how many absorbance units change we get, so that seems to make sense. Okay, next we want to use a modified form of the Beer-Lambert law equation, which is absorbance equals the extinction coefficient times the concentration times the path length, ECL. Now, when I say we're going to modify this a little bit, I mean we're going to include a change in time. So instead of A equals ECL, we're going to use A over T equals EL times concentration per time. So we're allowed to do that because we're dividing each side of the equation by the same thing, which is the change in time. So we have our A over T value here, which is 0.15 absorbance units per minute. We want to get micromolar substrate per minute. So we want the C over T part of this here. So the only real thing that we need here in order to do this calculation to get molar per minute, we'll take care of the micro part of that here in just a second. In order to get molar per minute, we need to divide by the extinction coefficient for the chromogenic product that is created during the enzyme assay, which is dopachrome, and that is 3,700 per molar per centimeter. So we're going to take our AU per minute there of 0.15. and we're going to divide by 3700, which is characteristic for dopachrome. It's not going to be the same value if you're testing another substance. So each product that generates color is going to have its own extinction coefficient. It just happens to be 3700 for dopachrome. Okay, so that's going to give us a really small number, but remember, this is in molar per minute. We want micromolar per minute. Okay, so we're going to take that, and we're going to multiply by 1 times 10 to the 6th, or a million. There you go. 40.5 would be your initial velocity here. So that is the V0 value that you are collecting, or rather that you are calculating for this particular substrate concentration. You're going to do the exact same thing for all the other substrate concentrations as well. Ultimately, we're not really going to use the absorbance numbers for anything except calculating the V0. We're going to need the V0 values when we eventually do our Michaelis-Menten plots. Okay, now let's skip ahead and actually assume we already have all of our Michaelis-Menten data here. So let me kind of zoom in here. Okay, so let's say that our substrate concentrations that we tested here are 0.05 millimolar, so everything's millimolar, 0.05, 0.1, 0.2, 0.5, 1, 5, 10, and 15. So we're testing a wide range of substrate concentrations. Let's say that we did all those calculations that we just did for each substrate concentration, and this is what we get in this particular graph right here. Ignore these columns right here. We'll talk about that in a minute. Okay, so we want to first create a Michaelis-Menten plot here, so we're going to do the exact same thing. We are going to create a chart, XY scatter, boom, you should get something that looks like this. It is not a linear plot. This is a hyperbolic plot. So this is a graph of the substrate or the initial velocity as a function of the substrate concentration, and we talked about the Michaelis-Menten equation during lecture. So you should see a pretty rapid increase in the initial velocity at the lower substrate concentrations, but as the substrate becomes more and more concentrated, you're going to saturate the enzyme and you're going to eventually hit a maximum velocity. Now, ultimately, our goal here for this amount of enzyme that we're using, and keep in mind your Vmax value is going to change depending on how much enzyme you included in your reaction, but for this amount of enzyme, we want to determine the Vmax and then also the Km. The Km actually will be the same no matter how much enzyme you add. So we want to calculate both the Vmax and the Km here. Well, how do we do that, right? So all we can really do using the Michaelis-Menten plot here is eyeball it, right? So it looks like Vmax is maybe around 30 millimolar up here, so 30 micromoles per minute. It's a little hard to eyeball, but it looks like we're kind of approaching 30 but never getting there. So it looks like Vmax is probably going to be about 30 micromolar per minute. The Km is the substrate concentration at which you get half maximal velocity. Well, it looks like it's about 15. If we kind of carry down an imaginary line down here, it looks like the substrate concentration there is going to be a little less than 1 millimolar. Okay, so we're able to eyeball these numbers, but we want to be able to precisely determine things. We don't want to get into the habit of eyeballing things in laboratory science. So that is why we are going to do a Lineweaver-Burke plot. So essentially, with a Lineweaver-Burke plot, we can use all of these numbers that we've already collected. We don't have to really do any new calculations, or at least any hard calculations. So what we're going to ask Microsoft Excel to do for us here is to give us the reciprocals of both the substrate concentration and the initial velocity. So we're going to take all those same numbers and we're just going to flip them upside down. Numerator becomes the denominator and vice versa. So for the substrate concentration, I'm going to say 1 over this right here. Okay, drag it down. Did one too many there. Okay, so there are those same numbers flipped upside down. So 1 over 0.05 is 20, 1 over 0.1 is 10, and so on and so forth. All right, I'm going to do the same thing for the initial velocity. Okay, and then come down here. Okay, so now we are going to do a Lineweaver-Burke plot. We're just going to take another XY scatter plot, except of these data instead. The Michaelis-Menten plot was substrate concentration against initial velocity. The Lineweaver-Burke plot is 1 over S against 1 over V naught. Now look what we get here. This is magical. Instead of having a hyperbolic plot, we get a plot that is almost perfectly linear, which is kind of a cool thing. So if we look at our R-squared value, 0.9938, pretty damn close to being a perfectly straight line. Okay, so what value do we get out of having a perfectly straight line? Well, there is a lot of information that we can infer from the equation of this line: the slope of the line, the y-intercept, and the x-intercept. The first thing that we are wanting to do here, like we said before, we want the Vmax and the Km, okay? So we said that with the Michaelis-Menten plot up here, we can eyeball those things. Well, what if I told you with the Lineweaver-Burke plot, we can precisely determine them? So here's the first thing that we can do. The y-intercept here for the Lineweaver-Burke plot is given as 0.0364. That is actually equal to 1 over the Vmax. So if I want my Vmax and I don't want to eyeball things, I would just take 1 over 0.0364, just like so. Look at that, 27.5 basically. So pretty close to that 30 value that we were kind of indicating before. It's a little incongruent with the data because we did get a V0 value of 28.4, but you have to kind of allow for some experimental error. So I just kind of pulled these numbers out of a hat, so try not to worry too much about that. The Vmax experimentally is pretty close to what you would think it would be. Okay, and then for the Km, there are actually two different ways that we can do this. The harder way, I think, is to make use of the x-intercept. The x-intercept is equal to -1 over Km. That's a little bit harder to do because we would actually have to use this equation, set y equal to 0, and then solve for x. So we can do that, but what would be easier is to use the slope. The slope is equal to Km over Vmax. So if I want to just get Km, I would take the slope, which is 0.0216, and multiply it times that Vmax that I just got. I get a Km of practically 0.6, which again is pretty much in line with what we see here. So at a half maximal velocity, if maximal velocity is 27, half maximal velocity would be, what would that be, about 13.7 or so. So at about right here, yeah, that makes sense. Maybe about a substrate concentration of 0.6 or so. So doing this, we can actually precisely determine the Vmax and the Km. There's a lot of power in the Lineweaver-Burke plot, even though this is not a perfectly linear line and the Vmax and Km might be just a little bit incongruent with the data, it still works pretty well. And it would probably work even better if I hadn't just pulled numbers out of thin air. Okay, so there's one more thing that I want to show you how to do here. So I want to show you how to use a Lineweaver-Burke plot to determine what kind of inhibitor is being used to inhibit an enzyme. There are three types of enzyme inhibition. There is competitive inhibition, there is non-competitive inhibition, and there is uncompetitive inhibition. Now, what separates these three modes of inhibition is how they affect the Km and the Vmax. And that, of course, is going to cause the Lineweaver-Burke plots to look a little bit different in terms of their slope, x-intercept, or y-intercept. So what I'm going to do here is I'm going to show you how to incorporate inhibitor data into the Lineweaver-Burke plot that we just did, and we can use that information to determine what kind of inhibitor that we've got. Okay, so I have included here some inhibitor data. Basically, we did the exact same experiment with the exact same amount of enzyme at the same substrate concentrations. We just did 2 extra runs using 2 different concentrations of a particular enzyme inhibitor. This run was done with 1 millimolar inhibitor, and this run was done with 5 millimolar inhibitor. So what I'm going to do here, I don't really feel compelled to plot them on the Michaelis-Menten plot. I wouldn't really get a lot out of that. So I'm just going to go ahead and move them over here to do our Lineweaver-Burke plots again. So 1 over S here. So this right here, I'm going to update this so that we know that this is without inhibitor, so minus inhib. I guess that'll work. This is going to be our 1 over V. We'll say that this is 1 millimolar inhibitor, and then I'll say that this is 1 over V. We'll say that this is 5 millimolar inhibitor. Okay, so I'm going to do the same thing I did before. I want the 1 over the V naught values. Do that. Bring that down here to get the rest of them. Do the same thing here. Bring this on down here. Okay, and now what I want to do is I want to plot both of those into the same graph. So the way that you do this is you want to go to Select Data. I right-clicked on the chart, so I want to go to Select Data. I already have Series 1 plotted here, so this is no inhibitor, so I'll go ahead and update that so it indicates that on the plot. And I'm going to create 2 new series. The first series we'll say is plus 1 millimolar inhibitor. There we go. I'm going to select my X values. That's going to be our 1 over S values right there. And then for the Y values, I want the 1 over V naught values for that particular concentration. There we go. Okay, and then I'm going to create another plot here. This is plus 5 millimolar inhibitor. I want the same X values. Those are the same substrate concentrations. So the substrate concentration is what you want here. The inhibitor concentration has no bearing on the substrate concentration, so don't worry about that. And then the Y values, I want these right here. Okay. There we go. Okay, so let me go ahead and create trend lines for these. I want the equations as well. Okay, there we go. So there's that one, and then let's get this one right here. There we go. Okay. Okay, so look at what we've got here, and let me shift the axes just a little bit just to make this a little bit more apparent. So I want to be able to see into the negative for our x-axis here. Okay, that's a little bit better there. Okay, so it's a little hard to tell. It looks like they're all intercepting the y-axis at 0, but trust me when I say it's not. That's not quite the case. Actually, let me update the y-axis so this will be a little bit more apparent. We'll lose some of the data out here, but I think you'll get a better idea of what's going on. So let's set the maximum on the y-axis at, let's say, 2. Okay, there we go. That's a little bit better. Okay, so if you look here, let's try to find. So the point, this one goes right here, and this one goes right here. Okay. So those are the equations for our 3 lines. The blue one is without inhibitor, the orange one is 1 millimolar inhibitor, and the gray one is 5 millimolar inhibitor. Now, if you look here, the y-intercepts are a little bit different, but they're pretty close to being the same. So really what I would have to conclude here is that the y-intercepts are practically the same, but let's go ahead and do some calculations here. So the Vmax and the Km that we've already calculated are for no inhibitor. So let's do the same thing for 1 millimolar inhibitor, and we'll do the same thing for 5 millimolar inhibitor. So let's calculate Vmax and Km for both of them. So for 1 millimolar, Vmax is going to be 1 over the y-intercept, so that's 0.0292. The Vmax, oddly enough, is up to 34.24. Okay, let's do our Km, so that's going to be equal to the slope, which is 0.1585 times the Vmax. There we go. Now it's up to 5.42. And then we'll do the same thing for this. Our y-intercept is 0.0687. 0.0687. There we go. Vmax is down to 14.55 there, so that's a little bit odd. And then the Kn is going to be equal to the slope, which is 0.4963 times the Vmax. There you go, 7.224163. Okay, so when we want to determine what kind of an inhibitor we've got, we want to pay attention to how the slope changes, and we want to pay attention to how the y-intercept and the x-intercept change. Now, even though you can see here that The Vmax seems to have changed a little bit. I would argue that the Vmax really has not changed very much. Keep in mind, these are not experimental data that we're analyzing here. These are just numbers that I pulled out of a hat. So it looks like they are all intercepting at about the same place on the y-axis. So honestly, I would conclude here probably that Vmax is not really changing much. So let's go ahead and assume that the Vmax is the same for all three. I know it doesn't look like that, but let's just humor me. Let's assume that they're all the same. If the Vmax was truly changing, I think we'd see more separation between these three graphs on the y-intercept, okay? So, but we can definitely see that the Km is drastically going up. So the Km starts out relatively small. The more inhibitor we add, the more the Km goes up, meaning that in order to reach maximal velocity, we have to add more substrate. There's only one kind of inhibition that follows that trend of increasing the Km but not really changing the Vmax, and that is competitive inhibition. So you can overcome a competitive inhibitor by just increasing your substrate concentration. So that would cause the Km to change. It would cause the Km to go up, indicating that the enzyme has a lower affinity for the substrate, but the Vmax ultimately would not change because you can still reach that maximal velocity as assuming that you get the substrate concentration high enough. And it is worth noting that I think these data would have looked a little cleaner if maybe we had tested some higher concentrations of substrate. But that's going to do it for this video, so I hope you found this helpful in terms of kind of figuring out how to treat your data. I know there's a lot of data to kind of look at. It's kind of hard to know where to start, but hopefully watching this video will kind of clear your head a little bit and give you an idea of how to progress through the data analysis here. So this is all I'm really looking for here. Take your data and do your best to make a conclusion about what kind of inhibition is occurring. That's all I can really ask of you at this point. I think you should be able to do it, even if your data don't look very good. All right, that's going to do it for this video. I hope you found this helpful, and I will see you next time.